The next three videos, starting from this one, will focus on advanced problem solving, and they'll be the last set of videos I'll make for the complex numbers playlist. Olympiads, this particular video is about Olympiad complex number problems, and Olympiads are international competitions with students from across the world, and the most ancient, so to speak, Olympiad is the Mathematics Olympiad that was founded in 1959, where high school students are tested in advanced knowledge of mathematics. There are Olympiads also for physics, chemistry, biology. They call it the Science Olympiad. Then there's now the Informatic Olympiad and now AI Olympiad. So let's see some of those, just some interaction with such kind of problems. So Olympiad complex number problems. First, let's start with the foundations, right? We've talked about this every time. First of all, we know that a complex number is z equals x plus yi, or sometimes a plus ib, or x plus iy, whatever you want to use, where x and y are both real numbers, but then I squared is equal to minus 1. So they take different forms. They can take algebraic forms where you have x plus yi, and then they can take polar forms where you have r into cos theta plus I sin theta, which can be derived from x plus iy. By taking the magnitude of x plus yi, you get r, and then by also taking arctan of y over x, you get theta, which you can then put together like this. And then you have the exponential form, which is rei theta. Since cos theta plus I theta is the Euler equation, being e raised by I theta. So that simply tells us that you can switch from algebraic to polar, from polar to exponential, from you can just switch between any two of these forms, depending on whatever you need. So the r we find here, like I said, is the modulus of z, z being x plus yi, and that is the same thing as square root of x squared plus y squared. And theta is the argument of z. And I said that theta is actually arctan of y over x, the inverse tan of y over x. Then we have key identities. Just like I said, now the Euler's formula is e raised by I theta equals cos theta plus I sin theta. And we have the De Moivre's theorem, to which we also considered in the process, and that is cos theta plus I sin theta raised power n. So if you raise cos theta plus I sin theta raised to power n, it's simply the same thing as cos n theta plus I sin n theta. So this helps to deal with very big powers of complex numbers, De Moivre's theorem. So with this now we can then easily take things back to to maybe polar form or algebraic form. So you switch forms based on the need you have at any point in time. Now all these foundations are important because they help us to be smart in solving complicated problems in Olympiads. Then we have 33.3. We have the geometry of complex numbers. First of all, we interpret z equals x plus yi as a point x comma y. And x, of course, is on the real axis, while y is on the imaginary axis. So we just use but we use the same Cartesian coordinate system for them, except that now x is real and y is imaginary. So the key ideas, we have multiplication. When you multiply when you multiply complex numbers, so you're causing rotation and scaling at the same time. When you conjugate, conjugation is changing the sign. So the conjugate of z, for instance, will be z bar, which is x minus yi. So when you conjugate, you have a reflection across the real axis. And then absolute value of z1 minus z2 will give us distance, just like we have in coordinate geometry. So let's start with some of the problems. Imagine you want to compute 1 plus I raised to power 10. If you have to do this algebraically, that's a lot of stress, right? Imagine you have to having to expand. We even have methods like we can use combination method, you can use general expansion, but it is going to be really a lot. It's going to be messy. But guess what? Because we can convert this algebraic expression into polar form via the De Moivre's theorem, then we have this. Or not, maybe not even via the De Moivre's theorem yet. We can convert this trait to polar form. So for instance, you want to compute 1 plus I raised to power 10. So first convert to polar form. How do you convert to polar form? Find the magnitude of 1 plus I. The magnitude of 1 plus I is square root of 1 squared plus 1 squared, which is square root of 2. and that is why you have r here. And then to find the argument theta, that is arctan of 1 over 1. Arctan of 1 over 1 is arctan of 1, and tan 45 degrees is what gives us 1. So it means that arctan of 1 is 45 degrees. 45 degrees is pi over 4. So it means this same 1 plus I is equal to root 2 into cos theta, cos pi over 4 plus I sine pi over 4. Then you apply the Moivre theorem. So to apply the Moivre now, so the Moivre theorem, we already saw that it says that when you have cos theta plus I sin theta raised to power n, it's simply the same thing as multiplying the angle, the argument by the power, and in both cases, and you're good to go. So here now you have, so first of all, if you raise this to power 10, of course, this root 2 is going to be raised to power 10, and then you have cos 10 times pi over 4, that's 10 pi over 4 plus I sine 10 pi over 4. So in that case, so root 2 raised power 10 is like 2 raised power half times 10. That's 2 raised power 5. And then 10 pi over 4 is 5 pi over 2. And 10 pi over 4 is 5 pi over 2 also. So you can then find cos 5 pi over 2 and sine 5 pi over 2. So you can even do that in Google. So sine, okay, let's do cos first. Cos 5 pi, that's 5 times pi divided by 2, like this. So that gives 0. So, this is 0, that will go. Then let's do sine now. So we have sine 5 pi over 2, sine 5 pi over 2, that's 1. So that means you have 2 raised power 5 multiplied by 0 plus I times 1. So that's why 2 raised power 5 is 32. With this I here, that's why you have 32I, basically. So imagine if you have to do it algebraically, that's a lot of stress. You have to do binomial expansion, and that's too much. So here you can easily, so to be sure that we are correct, you can just have 1 plus ij, 1 plus 1j, that's the same thing as 1 plus I, raised to power 10, and it just gives us 32j straight up. It gives us 32j like that. So we move on to, so that's one possible kind of problem you can find in Olympiad. So normally, if you are not informed, you will start expanding, and before you get like 1/4 of the way, somebody who understands polar form and the Morse theorem would have got the results already, and they would have moved to another question. So it's about smartness. It's because difficult, complicated problems sometimes have just simple solutions. So, but who people that don't know just go about stressing themselves trying to solve using some very uh, lengthy methods. So we talk about roots of unity, which I'd actually considered in very early videos, like 2 years ago. I just revived this after 2 years. So you want to solve z raised power n equals 1. So the solutions are usually z sub k equals e raised power 2 pi I k over n, where k takes values from 0 to n minus 1, 0, 1, 2, up to n minus 1. So, and then there's an important identity that we have 1 plus omega squared plus all of that, all the way down to omega n minus 1, omega raised by n minus 1 equals 0. So that's roots of unity. So let's take a practical example of that. So if you talk about roots of unity, then it means that we have solve if you have to solve z raised by 4 equals 1, for instance, just use this formula. So our z is usually e raised by 2 pi I k all over 4. 2 pi I k all over 4. So as you begin to vary the k's now, if k is 0, right? So it means we have e raised power 0. If k is 0, it means 2 pi I times 0 is 0. 0 over 4 is 0. So e raised power 0 is 1, like this. Then if k is 1, so you have 2 pi I over 4. Okay? And that'll be I. You have to do 0, 1, 2, 3 now, because here our n is 4. So you have to go from 0 to 3. So you have 2 pi I k over 4. So you put 0, you put 1, you put 2, you put 3. So when you put 0, you get 1. When you put 1, you get I. When you put 2, you get minus 1. When you put 3, you get minus I, like that. And these are the possible solutions you get when you solve z raised by 4 equals 1, like that. And that is why another way you can look at this is this. If you want to another approach to verify that what you have done is correct, you have z raised by 4 equals 1, right? That's the same thing as z raised to power 4 minus 1 equals 0. And then we know that this can be z raised to power 2. I mean, z raised to power 2, then 1 raised to power 2. And that is equal to 0. So if you want to do this now, it means you can say z raised to power 2 minus 1 into z raised to power 2 plus 1 equals 0. That's difference of two squares. Now, you still have another difference of two squares here. So that means you can have z minus 1 into z plus 1 here. But for this, this still another difference of two squares, because if you solve z squared plus 1, if you have z squared plus 1 equals 0, that means z squared is equal to minus 1. So z is equal to plus or minus square root of minus 1. So that means z is plus or minus I. So in essence, you can express this as z minus I into z plus I. And to be sure that is correct, you can just even try to expand. Z times z is z squared. Z times I is iz. I mean, z, that's plus iz. Minus I times z, that's minus iz. Then minus I times plus I, that is minus I squared. So that means you have z squared. This cancels out. Then minus I squared is something as minus is already there. Then I squared is minus 1. So you have z squared plus 1 like this. So that means this is actually true, that you can then say z squared plus I, is the same thing as z minus I into z plus I. All of that is equal to 0. So with this now, we have our four solutions. So from here, z minus 1 equals 0 implies that z is equal to 1. Then next, z plus 1 equals 0 implies that z is equal to minus 1. Then next, z minus I equals 0 implies that z is equal to I. And lastly, you have z plus I. So z plus I equals 0 implies that z is equal to minus I. And these are the four solutions for z raised to power 4 equals 1. So at least, even if this was looking somehow, you have also established it here. Now, of course, it was easy to get when you put 0, right? It was easy to get that. But when you put 1 for k now, so you have 2 pi I over 4. So, I mean, what you just do is just come here and do exponent. Exponents. So just say exponent for 2 pi I over 4. That is 2 pi. Okay, there's no I, the 2 pi I. Yeah. 2 pi I over 4, that gives I. And that is why we have this I. Okay? So you put 0, e raised by 0 is 1. You put 1, you have 2 pi I over 4. You put 2, that'll be e raised to, if you put 2, that's 4 up here. So 4 cancels 4. So you have e raised by pi I. So now e raised by pi I would give us e raised by pi I. That gives minus 1, and that is why this one is minus 1 here. Then you put 0, 1, 2, 3. You put 3, you have e raised to power 2 times 3, that's 6 pi I over 4. That's e raised to power 3 pi I over 2. Okay, that'll be 3 times pi times I all over 2, and that gives uh, minus I. And that is why we have minus I like this. So I've used two different methods to solve the same problem. And you can see we have the solutions like that. So then we talk about locus problems now. So we talked about locus. It's locus is actually a set it's a it obeys a set of rules, right? So if you imagine the example of absolute value of z minus 1 equals absolute value of z plus 1. So the interpretation here is that the distance from 1 equals distance from minus 1. And the result is that the result of the real part, real z is equal to 0 in this case, right? Um, so that's an example of a locus problem. So let's see. Let me do that and see what happens. So we have absolute value of z plus 1 equals absolute value of z minus 1. So of course um this is x plus iy plus 1 equals x plus iy minus 1. So what can we do with this now? We're talking about the absolute value. So That means you have x plus 1 plus iy modulus, then modulus of x minus 1 plus iy, like that. So we can square both. We can then take the magnitude. So that's square root of x plus 1 squared plus y squared equals square root of x minus 1 squared plus y squared. So if you square both sides, you get x plus 1 squared plus y squared equals x minus 1 squared plus y squared. So y squared cancels y squared clearly. So we have x plus 1 squared equals x minus 1 squared. If you take the square root of both sides, it means that x plus 1 is equal to x minus 1. Yeah, this doesn't make so much sense. So we have x minus x equals minus 1 plus 1, minus 1 minus 1. Okay, so this is 0, this is minus 2. Makes no sense, and that is why it's ended that the real z is actually 0 in this case. Okay, so doesn't hold water like that. So the result is that the real part of z has got to be 0 for that to hold. So like that. Then we move on to the inequality. We have triangle inequality. Absolute value of z1 plus z2 is less than or equal to absolute value of z1 plus absolute value of z2. I think I proved this previously, but in one of these three videos that ending this playlist, we're going to, I think the next one will be talking about proof-based problems. So for conjugate tricks, right, you want to simplify 1 over 1 plus I. So you just multiply by conjugate. So you have 1 over 1 plus I times 1 minus I over 1 minus I. So that's why we have 1 minus I over 1 plus I over 1 minus I. So you have 1 minus I now. 1 times, so just do difference of two squares. That's 1 squared is 1 minus I squared. That's 1 minus, I mean, I squared is minus 1. So that's 1 minus minus 1. That's 2. So you have 1 minus I over 2. So that means you have 1 over 2 minus 1 over 2i. So that's for conjugate. And then we talk about substitution of z equals e raised by I theta. So if you have z plus 1 over z, so let z be e raised by I theta. And then if you have z plus 1 over z, you have e raised by I theta plus e raised by minus I theta, because this is 1 over z here. And how do you do this? E raised by I theta. So to take care of that, right? How is that did we come about that? So you have z all over z equals 1 over z, and we want to like simplify this. So you can let z be e raised by I theta. No, r e raised by I theta. I suspect. Yeah, z should be r e raised by I theta. Okay. Uh okay, we can just substitute e raised by I theta here. So in that case, then we have z plus 1 over z equals e raised by I theta plus 1 over e raised by I theta. And that is equal to e raised by I theta plus e raised by minus I theta. Now we already know that e raised by I theta is the same thing as cos theta plus I sine theta. So for this other one, it means we have cos theta minus, okay, minus I sine theta. So cos theta plus I sine theta. So for this other one, it's cos theta minus I sine theta. So if we expand that, we have cos theta plus I sine theta plus cos theta minus I sine theta. So this cancels this. So we just have cos theta plus cos theta, and that simplifies to 2 cos theta. And that is exactly why we have this uh here, 2 cos theta right here. Now we go for geometric insight now. So if z1 plus z2 plus z3 is equal to 0, and the modulus of z1 is equal to modulus of z2 is equal to modulus of z3, then we can say that the triangle formed is equilateral. The triangle formed is equilateral. Then we talk about factorization. That was the kind of thing I did with z. That the second approach I used in solving z raised by 4 equals 1. That was like factorization method. So if you want to solve z cubed minus 1 equals 0, of course, we know this is a standard factorization for difference of cubes. So this is z minus 1 into z squared plus z plus 1 equals 0. And then from here now, So we have one real root here. The real root is z equals 1, and we leave that. But for non-real roots, we have z equals minus b. B is coefficient of z. So that's minus 1 plus or minus I plus or minus square root of d squared, which is 1 squared minus 4, 1, 1. That's 1 minus 3. I mean 1 minus 4, which is minus 3. Square root of minus 1 is I, and square root of 3 is here. Then all over 2a, 2 times 1. Coefficient of z squared is a. So that's 2a. So we then have z equals minus 1 plus or minus I root 3 all over 2. So we have that. Then we can also talk about arguments. So the argument of z1 over z2 is simply the same thing as argument of z1 minus argument of z2. And don't forget, argument of z1 will be arctan of y1 over x1. Argument of z2 will be arctan of y2 over x2. So in that case, then we can have, so for instance, look at if we have n raised power 6 and we are looking for roots. So if n is raised to power 6, like we are looking for z raised to power 6 equals 1, right? We're looking for those 6 roots. So the general formula, we have exponent of 2 2j, that's 2pi times 2pi times 2 pi I. The I now is this j here. Then multiplied by k over n, and our n is 6. So our k is going to be from 0 to 5. That's 0, 1, 2, 3, 4, 5. So at x equals, when you say uh, n, k equals 0, you do, of course, k equals 0 clearly is going to give us e raised by 0, which is 1. And that is why, so we have 1 here, and then we have, so as you go 0, 1, 2, blah, blah, blah. So you have all these other solutions when you run this particular one. So it's like you can actually use, okay, if I say n is 4, right, you're going to see all those 4 solutions we got the other time. So you see them, we have minus 1, we have minus 1. Okay, this is the real axis, right? And this is the real axis, this is the imaginary axis. So on the real axis, we have minus 1, we have 1, then we have uh, I and minus I along the imaginary axis. So real axis, we have minus 1 and 1. Imaginary axis, we have minus 1i, which is minus I, and then we have 1, which is I, actually. So just like we got the other time. But if you make it 6, so this code now can now help if you, even if you're looking for uh z raised power 10 equals 1. So you see the solution. Now it's now beginning to form beautiful stuff like this. So let me do 100 even. So it now becomes like a ring. Oh, this is coming out cool. So you can have all that. Even 1000, you can find it. So code now makes it pretty cool now. So the more you get the point, the more it forms like a circle like that. So but let's go back. Okay, let me even do 10,000. Oh, even 100, that's 100,000. That's a lot. Okay, so it's forming a circle more and more. So let me take it back to 6. We have this. All right. So then let's talk about some advanced problems. Some advanced problem. So we want to compute um summation from k equals 0 to n minus 1 for 1 over 1 minus 1 over 1 minus wk omega k, where omega is e raised power 2 pi I over n. So what we now need to do is step 1, we handle the problematic term. So the problematic term is when k is 0. So that is 1. It's problematic because this function will be undefined. So we have omega raised by 0 to be 1. And then if it is 1 here, so we have 1 over 1 minus 1, which is undefined. So we instead consider uh, summation from k equals 1 to n minus 1. So because at 0 it will be undefined, so we move on to k equals 1. So, and we now have, we pair terms. So we pair k with n minus k, so that such that we then have w raised by omega raised by n minus k equals omega raised by minus k. So we then consider 1 over 1 minus omega raised power k plus 1 over 1 minus omega raised power minus k, like that. And so the next thing is we simplify the pair. So if we simplify this now, so you take LCM, right? So you have 1 minus omega raised power k into 1 minus omega raised by minus k. So this cancels this. So we have 1 minus omega raised by minus k multiplying 1 to come here. Plus, this cancels this. We have 1 minus omega raised by k right here. So for the numerator, the top now. So we have 1 plus 1, 2, then minus omega minus omega raised to power k. Okay, both of them are negative, so you just have minus omega raised to power k plus omega raised to power minus k. For the denominator, we can expand. So when we expand, we have 1 times 1, 1. 1 times omega raised to power minus k. We have omega raised to power minus k. Minus omega raised to power minus k times this. That's minus omega raised to power minus k. Now we multiply minus omega raised to power k times minus omega raised to power k. That will give us plus 1 because minus times minus is plus, and then omega raised to power k times omega raised to power minus k is 1. So at the end of the day, we have 2 minus omega raised per k plus omega raised per minus k. So you see, these two are basically the same. So it means that we have 1 right there. So if we then count the pairs now, so we see that for this, we have considered we are pairing k with n minus k at the same time. So we have two pairs of that. So if you, I mean, we count pairs of that. So in that case, there are n minus 1 over 2 such pairs for odd n. Even n works similarly with a middle term that also evaluates to half. So the final result is just that summation from k equals 1 to n minus 1 for 1 over 1 minus omega raised by k is n minus 1 over 2. And the final answer is n minus 1 over 2. So that's the computation for this expression right here. Okay, so uh, in essence, we have our key techniques summary. First of all, when you have a problem, you want to convert it to polar form. Then next, you want to use roots. Uh, you want to use roots of unity symmetry, like the ones we did with z raised power 4 equals z raised power 4 equals 1, or z raised power 100 equals 1. We're using code. I was not able to show all this one that was forming like a circle. Then you can interpret geometrically. You can use conjugates when necessary, especially if you need to rationalize. Then you can substitute z equals e raised power I theta when you have to deal with things like z plus 1 over z. Then you can use argument properties. So we have some practice problems as usual, 20 of them. So let me show them in fives now. So you have 1 to 5 here. Then you have 6 to, we can see 6 to, okay, let me do 6 to 11. You have 6 to 11 here. We have 12 to 12 to 17, 12 to 17 like that, and then the rest. Okay. So, of course, of this, I'll be solving questions 3 and 20. So, question 3 says to evaluate 1 plus I raised by 2024. Okay, normally that's just impossible if you don't know polar form and the Morris method. That's just impossible. It's possible, but it's while in fact you'll be solving only that problem and the competition will be over. Then problem 20, you need to solve z plus z bar equals 4, where absolute value of z is 3. That is z is so it's a circle with radius 3. That's basically what that means. So let's go ahead and do all of that. Questions 3 and 20 as we begin to take this home. So let's start with problem 3. Problem 3, problem 3, we need to evaluate 1 plus I raised to power 2024. Okay, we want to evaluate that to evaluate So to evaluate 1 plus I raised to power 2024. So the first step you want to take, step 1, you convert to polar form. Convert to polar form. So, and that means that you have 1 plus I. Z is 1 plus I, right? So in polar form, right? In polar form, Z is supposed to be R RE raised to power RE raised to power um in fact since we've done this kind of thing before, I will even take it to um to exponential form. Let me just take it to exponential form, in fact. So you can convert to polar form. Polar form and exponential form are about the same. So convert to exponential form. So you can also see another dimension to it. So in exponential form, right? In exponential form, we have z to be r e raised power I theta. So now all we need is this r and this theta. So we then go for that. We know that r is absolute value of z, which is absolute value of 1 plus I, and that is square root of 1 squared. That's this real part plus the imaginary part. The coefficient of I is also 1, so 1 squared. So with that, we have square root of 2 like that, and that's all we need for that. And then we come to theta. Theta, we know that argument z, which is the same thing as arctan, or better, I like my arctan this way, arctan of y over x. That's arctan of, if you write this as x plus iy, so that tells us that x is 1 and y is also 1. That's what we used here already. So that's arctan of 1 over 1. That's arctan of 1, which is arctan of 1 is 45 degrees, or in radian, that's pi over 4. So if that is the case now, uh, we can say, so, okay, let me change. So we can say that z being r I raised power theta is simply r root 2 e raised power I theta. Theta is pi over 4. Okay, that's it in polar form. So we have z equals root 2 e raised power I pi over 4, like this. Now, what do we need? We need, as what we call z now is raised power 2024. So we can then go for that. So z raised power 2024, which is the same thing as I 1 plus I raised power 2024, can then be taken to be is then the same thing as root 2 e raised power I theta, e raised power I pi over 4, all raised power 2024. So that's the kind of thing we have there. So how do we deal with that? So we have this to now be, that'll be root 2 raised power 2024 on one hand, then e raised power I pi over 4 raised power 2024. So because this one is a number, you just have root 2 is 2 raised power half, raised power 2024. And then e raised power I pi 4 now, e raised power I pi over 4 multiplied by 2024. Okay, so that means we have 2 raised power 1 over 2 times 2024 on one side, then multiplied by e raised power I pi over 4 times 2024. In fact, maybe this exponential form is even sweeter than the polar form. Polar form is cos theta sin theta. We can still convert this definitely. So this is 2 raised power 2024 over 2, that's 1012, then multiplied by e raised power I, then 4 goes in 2024, 4 goes in 2024, that's 4 in 20, that's 2024 over 4. Okay, well, let me just do, this is 1012 over 2, that's 506, like that. So that's simply 506. So we have I pi multiplied by 506. So that means we can simply just have this to be 2 raised power 1012 e raised power I 506 pi. So if you now like, in you can then write it um in the polar form now. So far, okay, I've only taken one step since. So normally, I've already assumed step two. So this is step two right here. Step two. Step two, we apply the Moivres. Apply the Moivres theorem. That's what I've been applying. Then now I go to step three, where we now convert back to so step three now. Step three, um, we simplify. Okay, convert convert to polar form. Okay, let me just call that step 3. Convert to polar form. So we know already now that 1 plus I raised to power 20, 24 is equal to 2 raised to power 1012 e raised to power I 506 pi. Okay, and that is, so if you to write it in polar form now, that's 2 raised to power 1012 into cos 506 pi. Okay, cos 506 pi plus I sine 506 pi, like this. So we have that. Um, so the next thing is to simplify. So I can call that step 4 now. Step 4, simplify, simplify trig values. Simplify trig values. So we know that 1 plus I, this has been just being finicky, being too elaborate, but it's okay. So this is 2 raised by 1112, I mean 1012 rather, cos 506 pi plus I sine 506 pi. Okay, so we need to do this. 2 raised by 1012. So what is cos 506 pi? As usual, you can use Google. So I come here again, cos. So, okay, I mean, if you're starting afresh, right, you can just do cos. Okay, it's even giving me option already. 506, 506 times pi. Cos 506 times pi. That is 1. I mean, as big as that is 1. And sine, we do sine for the same thing. Sine 506 pi. That is 0. Okay, so no matter how big it gets, everything ends up being 0 or 1 in most cases. So the first one, so cos 506 pi is 1. Then I sine 506 pi, that is I into 0. Okay, so we then have 2. So this now is equal to 2 raised by 1012 into 1, like that. So we can then conclude that therefore, therefore, 1 plus I raised by 2024 is equal to 2 raised by 1012. And that is just what that is. So if you try to do it algebraically, you're going to be there forever and ever. So, but it's good to know these fast ways. So let's go for problem 20 now. Problem 20. So for problem 20, we want to solve z plus z bar equals 4, where the absolute value of z is equal to 3. This is a circle of radius 3 in short, a circle whose center is at the origin and the radius is 3. So we go for step 1. Step 1. So we let z be equal to x plus iy, so that z bar can be x minus iy. Z bar is simply the conjugate. So, um, so then we say z plus z bar is equal to x plus iy plus x minus iy. That is x plus iy plus x minus iy. Minus iy cancels plus iy. So z plus z bar is 2x. So now that we have that, so we are solving z plus z bar equals 4, right? Um, so we go for step 2. Step 2. Step 2, now we can use modulus. So we use modulus. Um, so using modulus tells us that, okay, this is already 2x, right? But then we have modulus of z equals 3, right? So we use modulus. So modulus of z equals 3. That is given. And then we know that that is modulus of x plus iy equals 3. And that means that square root of x squared plus y squared is equal to 3. So in that case, then we know that okay, we can okay, we already know that this z plus z bar is equal to 4. I think we are given that already. Yeah, it's equal to 4. So this is equal to 4. All right. So this implies that this is equal to 4. That means that x is equal to 4 over 2, which is equal to 2. So we know x is already 2 from here. Okay. So we have x equals 2. So because it's going to be very useful here, so we have absolute value of x squared plus y squared equals 3. That's from the second part of the problem, this one here. So this first part is what we did to get x to be 2. Then using modulus now, we then have this other one, square root of x squared plus y squared equals 3. But we know x already. Um, or better, I mean, we can take square root, we can square both sides, right? So we have x squared plus y squared equals 3 squared. When we square both sides, that is, if you square this and then you square this, that takes the square root away. So that takes the square root away from that side, and then we have what we have in this next line. So that means we have x squared plus y squared equals 9. But you can recall that x is equal to 2. Recall x equals 2 from what we got here. So we can then substitute that. So we have 2 squared plus y squared equals 9. So that means that 4 plus y squared equals 9. That means y squared is equal to 9 minus 4. And that means y squared is equal to 5. So meaning that y is equal to plus or minus square root of 5, like that. So we got x to be 2 and y is plus or minus root 5. So we can then talk about the final answer. So final answer, final answer is, so we are solving this is an equation we are solving now. So we need z from that, right? So because we have z to be x plus iy, right? We have found x, we have found y. So that means z is equal to x is 2 plus or minus iy. I mean, plus or minus iy. Y is root 5. So we can finally write that. So z can be 2 plus I root 5, or z can be 2 minus I root 5. And that is what we need for that. So with this, we come to the end of this interesting video about solving Olympiad complex number problems. Again, let me flash the questions, try your hands on them and see how well you understand, what we have been doing. Let me know. Okay, this is 1 to 5, right? This is 6 to 11, 6 to 11, and then 12 to 16, or better still, 12 to 17, and then the rest. So let me know how helpful this is for you. And if there's something else you'd like me to talk about, feel free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. But if you have not subscribed, why not go ahead and subscribe right now and hit the notification bell also, so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like seeing some videos first before other people, or seeing some videos exclusively that no other person sees because you're a member of the channel. You can also request for PDF copies of my notes for your personal use. We can hang out together online or physically to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.